Hi, I'm going to take you through an example of solving problems for using a vector addition diagram when the forces are balanced. So the example I'm going to do is your cousin Throckmorton pulls a box at a constant speed across the floor. That phrase constant speed is what tells me that the forces must be balanced. This problem also tells me that he applies a 200 Newton force at an angle of 30 degrees. So the first thing I'm going to do is draw a free body diagram for this situation. So I'm going to go ahead and start with that force of Throckmorton pulling, which we're told is 200 newtons. I'm also going to add that 30-degree angle. Now, I know that as long as objects are on Earth's surface, there's a force of gravity. And right away, this is something that I can put a number to, because I know the force of gravity is m times g. And we're given that mass is 50 kilograms. And we know that as long as we're near Earth's surface, g is 10 newtons per kilogram. And so that force of gravity must be 500 newtons. Now, the other forces I need to think about aren't ones that are named directly in the problem. But that box is sitting on a floor. And so it must be compressing the surface of the floor a little bit, which causes a normal force. And then as that box slides, unless the floor is frictionless, that box is going to cause some shear across the surface of the floor, which is going to be a force of friction. The next thing I'll do is rearrange my free body diagram into a vector addition diagram. And so I'm going to show all of the same arrows, but instead of drawing them all starting at the same point, I'm going to draw them tip to tail from each other. And I know that because this object is moving at a constant speed, that it has balanced forces, which means my vector addition diagram has to be a closed shape. Whoops. There we go. And you'll notice that as I draw my vector addition diagram, I'm transferring over all of those labels. Now, it's important to note that the vector addition diagram is not just a useful diagram for problem solving, but one that's useful for reasoning. For example, I can already predict just based on my vector addition diagram that the force of gravity must be larger than the normal force in order to make this a closed shape. All right, the next thing I'm going to do is go ahead and solve for some numbers. Figure out how big some of these forces need to be. And I'm going to start with the force of friction. So as I look at this shape, this side that represents the force of friction must be the same length as this portion up here, which is the base of a triangle where that tension force is the hypotenuse. And so if I use SOHCAHTOA, that side is the adjacent side, which means if I do the tension force times the cosine of 30 degrees, I should get what that force of friction has to be. And so as I type the tension force of 200 newtons times the cosine of 30 into my calculator, I get 173 newtons. And so that must be my friction force. I can also find how big that normal force must be. Now, one way to think about this is that the normal force is equal to the force of gravity minus this chunk needed to make the vertical side of the triangle. So my normal force is equal to Fg minus that tension force times the sine of 30 degrees. And then I can plug in numbers. And when I put all of that into my calculator, I get that the tension force is 400 newtons. And something I like to do as just kind of a check, so I'd predicted earlier that the normal force should be smaller than the force of gravity. 400 newtons is indeed smaller than 500 newtons. Now there's one other number I can calculate based on what I've done so far, and that's the coefficient of friction. So when this box is sliding across the table, that kinetic friction is going to be at its maximum value. And so I can say that the force of friction must be equal to the coefficient of friction times the normal force. Therefore, that coefficient of friction must be equal to the force of friction divided by the normal force, which is 173 newtons divided by 400 newtons. And when I put all of that into my calculator, I get 0.43 for my coefficient of friction. So there you have it. Here's an example of how you can solve problems for balanced forces using vector addition diagrams.